we're live. Don't. Hold it, there used to be a gap there. Maybe I should take a desk out and put it somewhere else. Because I don't need 24 desks in the classes anymore. And the whole tuck and roll doesn't really need to be done. Hey Ryan, join the class. Excellent. You can help them with their Bohr model. "30 seconds. Hold it, did I open the right one? I did. And we were here, and then we got up to here. Oh, we haven't done this. Oh yeah, we gotta move. We gotta move. And oh, now I'll quickly do attendance actually. Attendance we are. Let's see. Attendance. Anders.
Yeah.
Hayden.
Here.
Esther.
Yeah.
Hillary. Hillary Stone. Absent. Jennifer. Jennifer Schoen. What? Oh, there we go. Jojo.
Yo.
Julian Chan.
Here.
Julian Gigi. Liam.
Yo.
Lucas.
Yo.
Mirhat. Mick.
Here.
Oliver.
Here.
Riley. Vienna.
Here.
Zachary.
Yep.
Did Hillary walk in while I was talking? No? Okay, we are definitely not there. So, pardon? At where? Oh, that doesn't matter. If you miss class due to sport, you are still bad. Because you had a choice. You could skip sport, or you could skip class. And they chose to skip class. But this is science class. Every teacher thinks that their thing is the most important thing ever. Okay. Oliver, you get to join any group you want. Please grab a partner and a whiteboard pen and find a spot at the board. Your partners have been assigned. Go find that person. Learn a name if you need to. Okay. Oliver, where are you? Okay, that sounds good. Get to the board, grab a whiteboard pen. Yeah, Jojo, where are you? There you go.
What are we doing?
Have you, oh, grab a whiteboard pen, find a spot on the board. I also have boards at the back. Here, let me very carefully show you something. If the front is too crowded, because I don't have all my whiteboards yet, I put some at the back. You're allowed to work at these. And let me run over here and quickly erase the answer. Excellent. What? Oh, grab the whiteboard pen. Excellent. What I would like you to do, oh yeah, you might need your dad's tables, by the way. What I would like you to do is I would like you to draw a Bohr model of boron. I want you to label the electron shells, the outermost shell, the valence shell, the valence electrons, the inner electrons, the inner energy levels, and the nucleus.
What is valence?
I have used all of those terms because some of them are duplicates. So I want to know if you know their equivalent or not. And if you don't know what some of them are, ask around. You're allowed to look at each other and consult and do things. Draw your own. Ryan might know a few things.
Are we doing neutral atom?
Pardon?
Neutral atom or ion?
It did not say ion in any way at all. Also, I want you to think about the type of Bohr model you're drawing, and it isn't the most efficient. So you want the electron shells, the outermost shell, the valence electrons, the inner electrons, and the nucleus. And you want the electron energy levels, the valence shell, the inner energy levels. Do not draw it to scale. Does anybody know why you don't draw it to scale? Why?
Because then you'd have the nucleus over here and the electron will be somewhere in the other one.
Yeah. Well, not even like if that was the size of the nucleus, that's actually fairly big to do it. I would have to draw the nearest electron.
Bye-bye. Okay, lock the door, lock the door. And lock me out. Oh, God.
I had to run all the way. It's about 2 football fields away, just to put that electron on a tree. So if you go that way, go down Mill Bay Road, you'll find a tree. It's got a tiny little dot I put there to represent the electron. That would be to scale. So little smaller is okay.
So electron shells,
So these are electron shells.
electron energy levels. Oxygen, that's it.
They're also.
No, do like connected to the orbit.
But they're also.
Electron shells,
It's also energy levels. These are energy levels.
valence shell. Which do you want to
Outermost shell. Oh, and the valence shell. Why is there a gun here?
Oh, it's for chemistry 11.
I'm sorry. If it's for chemistry 11, who are you shooting?
Oh, we don't shoot. It's for accuracy and precision. So, like, if someone's going to shoot at you, are you actually in danger if they're high accuracy versus high precision?
Inner electrons
Is it
versus
different?
energy
No,
levels,
no. I actually didn't know if it was.
nucleus.
Does it work?
Well, it's just a little dark.
Can you
It's
just shoot it
dollar
that way?
store.
Yeah, can you shoot
What?
at the wall?
No, from here, that will not reach that far. If I shot from here, I'd have to like adjust, and even then, I don't think it'll make it. It's very sad. We literally go 3 feet away for that particular chemistry.
Can I blow that?
No, it's dollar store. It's
Inner
not even good.
electrons, inner energy levels. Wait, the dollar store in this. And then you can
Yeah, it's like
I
uptown.
don't know what I buy one because I bring it. And inner electrons.
Yeah. If you buy anything you shouldn't have, and you horseplay in the house in a way that causes danger, your house parent will take it from you and not give it back.
And don't think
Or
this
give it
is
back in a
capable
break.
of being
Can we,
dangerous.
if we, if we all
No, no, no.
can we shoot each other during class?
No! Once you've got yours labeled, you can have a seat, have as many terms labeled on it as possible. You can consult others, look at other people's labels. You know where the nucleus is. You know where the, oh, you've got more labels.
Same thing, probably, no.
Excellent. Okay, I only saw that one. I didn't see this one.
That's what I thought. We plan on having this back.
Everybody seems to have the basic Bohr model done, so I'll just do that as a beginning. 5 protons, 6 neutrons. Now what do you got? You got Once you got all the labels, check them all off. Have a seat.
Electron shells. Electron energy levels.
We're missing something. We're missing,
Valence electrons.
oh, do we do that? No.
That's probably just the outer shell.
Yeah, no, it's been, these are
What if-
valence electrons.
Oh yeah. So it's just an air.
Yeah, that makes sense.
What if I put a cell phone blanket here?
Yeah, I'm good. Yeah.
Julian? where's your black shoes?
We needed to like go on a walk and our teacher just told us to wear normal shoes for the day.
Did this teacher email your husband?
Miss had to, I don't know,
Mm.
said to write it.
She is a house parent. She might have, but I just didn't see it. I'm always hesitant when I hear the word Ms. Hedquist because she is way more organized than I am. If it's supposed to be done, she will have done it a month ago.
She's a host parent on an island.
Oh, yeah.
So just draw a square around the
Square around the bees.
Yeah. Don't we need it?
Oh yeah, we do need it.
Yeah.
What do you need?
Square around the element symbol.
Why?
It makes me
Oh, yeah, sure. Okay. I thought, like, it's not
Like, it's not
required
necessary,
for it, but yeah,
may as well.
yeah, it makes it look sharp. Okay, Ryan, you're now proving a distraction. You have to go away. You can't just give them, engage people in conversation. No, Ryan. Sorry, you
I'm
have
at
to go.
Saturday school.
And then I get to close the door on him. And he can just look sadly. Oh, I need those. Those are really good. No, seriously. They go.
Why did you need that next to
You take chemistry
Why
11, we'll
is
find
that?
out. Okay.
I don't want to take chemistry 11.
Outer shell valence electrons, electron shells, electron energy levels, energy level. We got 5 and we got 6. We got nucleus, we got electron shells, valence electrons. Excellent. So I know some of them don't have valence in the right spot, but it looks like most people got there in the end. The chief one with valence is always on the outside, so they're always the outermost one. And the reason we give them a special name is because they're the ones that do all the work. All the chemistry happens with the valence electrons. The locked in inner electrons, they never do nothing. They stay on the inside, and they're just there. Their functions you'll learn a bit more about in grade 11. If you have a lot of them, they actually do some like blocking function, which affects the valence electrons, but they don't actually go anywhere. Is it valence electrons, valence shells, inner energy level? You can say, yeah, we're doing well.
Are you okay?
Why? Did I just say weird words and you think I'm having a stroke?
Kind of.
No, it was good. You know, if I ever start doing that, it is weird hearing someone who's having that kind of stroke because they think they're talking normally. In fact, I could be doing it right now, and I wouldn't know. But you'd be hearing like pineapple bread tonight, and you'd be going like, "What is he saying?" And I would think I said, "You know, get out your notes." Boron, nucleus, inner electrons, valence, electron shells, nucleus, inner electrons, outermost shell, electron shells, inner shell. So whoever did that would just know where the valence are. If you're missing the valence, and nobody would go there. So the duplicate amount, in case anybody's not here, which there is one person, so I should probably do it in for the live stream. Looks like everybody had it. So this is the valence shell, and it is also the outermost shell. That's the inner shell. And shells is also equal to an energy level. So everywhere where I say electron energy levels, that's the exact same as a shell. So if you've labeled the valence shell, you've labeled the valence energy level because the position of the electron determines its energy. Just like if you're at the top of a mountain, you have lots of energy because you have lots of potential energy, you could roll all the way down. And if you're at the bottom of the valley, you have very low amounts of energy because you can't roll anywhere. You're at the bottom that you can be. So higher energy, lower energy. Label the nucleus for those who are not here. Inner energy levels, nucleus, inner electron, inner shell. That's specifically the inner electrons, and that is specifically the valence electrons. Special word for them. Electron cells, outermost shell. I think I got all the things. Anybody notice I'm missing anything?
You're missing a minus on E3.
Oh, I am. Thank you. If I go like this, no one will ever did, and I will say I never even made a mistake. I've only made a mistake once in my life.
What if the E's look like a C?
Pardon?
What if the E's look a lot like a C?
That's not a mistake. That's just your eyesight.
Can you try checking it with the autocorrector tools that we can come with?
Oh, it'll do everything. It's
Just make it
the
small.
autocorrect can't do diagrams. It thinks lines are L's, so it'll actually make it. You can't even do that with it. But if I go like this, and I go group, ungroup, and then I specifically pick up.
I think you just erased one of the minus signs.
And then I group it. Oh, now look what you've done, Mr. Neufeld. Nope, I just want this one now. Come on. Oh, yeah. Oh, close. Forget it. We'll just do that.
Good enough.
Good enough. But I'll take that one now and text recognize it. Recognize. Oh. 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 It turns out a computer without eyes can see better than you can. Oh. Oh.
I guess they can recognize that there's an income tolerant.
It's also like AI literally isn't reading anything at a fundamental level. It does not know the words you're typing in. It only sees numbers that are associated with a probability, and it actually doesn't read it, which is why right now if you type into ChatGPT how many R's in strawberry, it will tell you not 3. It'll give you a bunch of answers. It'll never say 3 because it takes the word straw, and that actually has a code. It's a word fragment, and it says berry, and that's a word fragment, and it takes those two fragments that you put together, and it makes all the other things about spelling, and then it calculates a result based on probability. What is the most probable other fragment that would come up? And then it usually says 2. And that's why it can't tell you the answer. It actually doesn't read the word. If you spell it out, it will. That's why ChatGPT gets some things wrong. There's a new model out that seems to be doing better at that. We will see. I, for one, welcome our time-traveling robot overlords and would never say anything bad about them. Okay, isotopes. This is a brand new page. Please open it up in your notes. Isotopes have the same protons, but a different number of neutrons. Isotopes are present naturally. There's often, and sometimes the rare ones are radioactive, and we do cool things with them, like building nuclear power plants. Hold it, where's my... Excuse me. So if you have the same number of protons, you're the same element, but you're like an isotope. It's like I have a twin brother. His name is Scott. We look exactly the same, but he's a lot thinner than I am. He has a six-pack, which is like sad and pathetic, because what's better than a six-pack? Whole keg. So we have different masses. We are isotopes of each other, because as we all know, identical twins are identical in every other way, including memory. Yes?
By the time that you reach your age, so if your cellular code degraded slightly, so you are slightly different.
Your cellular code is actually degrading from the moment you were born. The ends of your chromosomes, called your telomeres, every time they duplicate, a little bit is snipped off the end. It's considered your natural clock. And when they start, and a lot of it's junk, but when it starts carving away at the actual genes, that's when you get like old age disease. Some animals, like those turtles who live for hundreds of years, actually have enzymes. This is a natural process. We think it's to actually age out the parents so you don't compete with the children, because they're the best chance for survival in a competing disease universe where if the parents kept living, then diseases would evolve against you and wipe out the species. So you need new variation, and that's your children, so it needs to get rid of the parents. This seems to be how. But turtles actually have an enzyme to specifically repair it. So it both does it and then repairs it. However, I know researchers who are working on that enzyme. It's like, would you like put it into yourself through like biomedical engineering and like make yourself, would that be possible, and would you do it? And they're like, all of them are like, no, I would never ever do that.
Why?
Because that particular mutation, the ability to do that, is also found in every form of cancer. So you probably give yourself super cancer rather than live, because it's all carefully balanced in the turtle. But if you just did it randomly, probably super cancer. Or, I just thought of this, Deadpool. I'd take it if there's a reasonable chance I could become Deadpool. Super cancer and super healing. It's literally Deadpool. I never thought of that until just now. Okay, these are the different forms of hydrogen. This is how we write the protons and neutrons, because this is not the atomic mass, but what is the word we use for the protons plus neutrons when it's not an average? Yes? No? There was like a gesture in the hand here. Yes? Mass number. Pardon? Hydrogen's mass is equal to 1 in this classroom right now. And that's its normal mass. How many neutrons does hydrogen 1 have?
0.
Did you? Pardon? None. So hydrogen 1 is just like, if you have hydrogen, it's just, I don't know why I started to write the names. You just have a proton, it's positive. In fact, if you have hydrogen 1 and it's +1 charge, that means its electron is gone. All you have is a nucleus. It's a single proton, and we call that a naked proton because it doesn't have the electrons anymore. And that is essentially what an acid is. And the reason acids are so powerful is because that charge is, now the electrons are gone, it's actually really small. And so all that charge is concentrated in a really tiny area and makes it really good at ripping things apart. Now this hydrogen is pretty rare. We're talking like parts per trillion, I think. This is known as hydrogen 2. It has a neutron, a very rare form of hydrogen. This is hydrogen 3. This is a very rare form of hydrogen that has 2 neutrons. This is known as tritium. We give it a special name just for study purposes, but it's still just hydrogen. And this is deuterium. Fancy names for 2 and 3. There's a World War II story that goes with this. I'll do it when I do uranium. What do I need to do with this? Oh, right. So that's where the mass number goes if you write the symbol. So the symbol is mass number on top. If you want to be really clever, you can put that there. The one on the bottom on the left is always the atomic number. You almost never have to write it, but it makes it easier if you're doing nuclear calculations. But since you know the element, you always know the atomic number because you can look it up. But if you're doing nuclear calculations, it makes things a little easier to include it, so that's where you put it if you have to.
What does H2 say?
Oh, deuterium. Thank you for asking, and I will try to text recognize it. Is it? Oh my God, it got the arrow. That's never happened before. That's pretty. That's.
Do you want the atomic parts?
Well, this is a part of the normal keyboard symbols because that means a carriage return or the return or the enter button. I said carriage return because in the olden days that's what it was called because it was based on typewriters. This is going to get. It got the 1 and an arrow.
Not bad.
That's not bad. All I have to do is take the green and go like that, and then we're good.
See if it doesn't do that.
No, I want to move on. So mass number on top. The other way that we do it is we write the mass number at the end. And it's just as the number. So hydrogen 1. And we read it as hydrogen 1. So this is hydrogen 1. This is hydrogen 2. And this is hydrogen 3. So if we write it out, we put a dash and the number. And that number is always the mass number. Also the story, as a heads up, it's a World War II story. Not everybody lives. But it's not terrible like the carbon monoxide story. And okay. Oh, and then I redo it there. There's the mass number, there's the atomic number, that's what it looks like. I will tell you as you do this, if you could calculate for each one, and I'll ask 2 random people using the app, calculate the number of neutrons for each of these uranium given those two numbers for each. Also, which one's the dangerous one? Does anybody know? 238 is the heavy, non-radioactive one. So the dangerous one is the 235. It is present in small amounts in regular uranium. This one is not radioactive. I wouldn't say it's safe in that, much like lead, you wouldn't want to eat it. But you could like make things out of it. In fact, the Americans, for the World Cup, made their sailboat and it had a keel of pure uranium. And the reason they did that is the keel, which is holding the boat steady, could be made very thin and strong because it's so dense. It's denser than lead. And so you could have a lot of weight, but not as much friction. So the boat could go a little faster. And it was what they call, not purified uranium, it's D something uranium. It's where they've taken all the 235 out, so it's not radioactive anymore. Both of them have exactly the same properties. They only differ in that tiny bit of mass. The World War II story is that, of course, the film came out a few years ago, in which all about the story of Los Alamos and the Allies making the first, doing the research for the first nuclear weapon. But why did the Allies develop it first? Because the Nazis also, at the time, were actively researching nuclear weapons as well. In doing so, the Allies didn't know where their research facilities were located. So they wanted to find out. So they told all their ships, all the ships taking supplies, all the submarines that are going all over the world, wherever you go to a new place, take a water sample. Bring it back, we're going to look at it. And what they did is they found an area that had too much hydrogen-2, because if you are doing nuclear experiments, you want to shield yourself against that radiation. A really fast, effective form of shielding is just to put a lot of water in between it, because you can pipe the water away when you don't need it, and you can fill the tank back up when you do, and it will block the radiation. If you block it with an extra neutron in the hydrogen, it just makes it that much more dense, and it's a bit better to block it. So you're using a lot of deuterium water, really rare, not present in high amounts, they have to purify it for somewhere. But there's an area in the world where there's too much of it. So they're like, So in terms of the world, this is the world. That is Europe, more Europe, Africa, Canada, States, South America. And then here is where they found it. They found it in Norway. So let's go. This is Norway. By the way, my geography and drawing skills are terrible. I was an adult before I learned that Korea was not next to Norway. I thought it was because a teacher casually mentioned, or at least that's what I heard. I'm guessing they didn't actually say it. They said that's where all the peninsulas were. So I thought that's where all the peninsulas were in the entire world. So I just assumed that's where Korea was. I always wondered how the Korean people got there, because they didn't have to travel overland or something. How did that happen? It was very confusing to me until Ms. Walensky found out, and she laughed at me. Anyway, this is Norway. So it's like a stick, and it's got it probably doesn't really look like that, but I don't know. There was a river we should draw that in blue, in Norway. And the Allies did know if you're trying to build nuclear weapons, you needed a lot of power, you need a hardened facility, and you need lots of research labs. And there was a dam, a hydroelectric dam, across a river that has power, has lots of extra buildings, and the Nazis have taken over Norway, so they know they have access to that. So in terms of where they found the samples, they found all the samples right out here. So there's too much, it must be coming out of this river. If it's coming out of this river, they must be at that dam. Yes?
We don't have to draw that.
You don't have to draw this. Yeah, when I go on a rant, you don't have to draw that. So Allies are like, we need to slow them down, so we develop nuclear weapons first. First come, first served, essentially. So they're like, okay, you can only access the dam from this side. So we're going to drop in some of the airborne into this side, SAS style, really good at hiding. There's some random towns in here. They're like, avoid the towns because if the Nazis know we're coming, they're going to prepare and we're not going to be able to blow up the dam. So they drop in the airborne and some wind picks up and they land here. Wrong side. So what do?
Try again.
Yeah, what do those people do?
They die.
Yeah. They because mission number 1, blow up the dam. Mission number 2, don't get caught. Can't blow up the dam, can't get caught. So they avoided the town, found a cave, and just waited there while they froze to death. Weren't going to be rescued in time. It was too cold. They didn't have enough equipment. They didn't even steal equipment because they didn't want anybody to notice and think there was people in the area. So, okay, forget them. Put in another team. They ended up on the right side. They traveled to the dam. They blow up the dam. The Nazis have to move their research. They don't have access to that area anymore. And they pushed back their program probably 7 to 8 months. And that was one of the reasons why there's 2 different speeds with the research program. We know a bit more, but not officially. Some of it's still secret. Because, of course, after the war, all the scientists that were working on the Axis side, where did they go?
America?
Yeah, the U.S. was like, hello, you did some research. Some cases, really terrible research. Would you like complete immunity and you can give us all of your research and continue working? And they went, would I? And then they all went to the U.S. and Canada. I used to think it was just the U.S., but I found out Canada was involved too, and that's why we had people doing unsavory experiments at the Toronto hospital during the Cold War on civilians. But that's a completely different story for another day. So, isotopes are fairly important. That is the one that actually blows up. If I could get, that's probably more than enough to calculate the number of neutrons. I'm going to ask someone randomly. Let's go here. Jennifer?
Is it 146?
146. This one? Excellent. Makes sense to me. Sorry, when I go like this, I think I'm getting a bit of a cold. I might be. My ear canals are quite, not that you need to know my medical information, but when I get a bit of a cold, I get stuff up. My ear canals actually squeeze shut, and I get a little deaf. So I go like this. It just means I can't hear you speak up. Anders, next one.
I don't know.
What does that number represent?
The atomic number.
That's the atomic number. So that's the atomic number. Pardon?
Mass?
That's the mass. So if that's the mass, and this is the number of protons, how would you get the number of neutrons? Subtract.
So I was walking to the story.
That's okay. Just quickly do it. While you're doing it, I'll tell another story. For years, they don't do it anymore. The Atomic Society, which is all the physicists who know things about atomic weapons, would run a summer program where they'd hire a grade 11 student, grade 11 physics student, and they'd hire someone deliberately who wasn't fantastic. They'd be like a solid C plus B student, not an A student, not someone who's like, oh, look how great I am, I took AP. No, regular physics student. They'd hire a few, and they'd say, over the summer, we have a research project. We're going to pay you to do this research project using Google, your local library. They started this before Google existed, but they continued until a little while after. And so at the time, lots of people early on were just using their local library. And they said, develop a working nuclear weapon. Just the plans, obviously. We don't want you to go get the material, but develop a working nuclear weapon. And in almost every case, they did. It's not hard to make. If you have the uranium-235, a nuclear weapon is really easy to make.
I'm sorry, I can't read what the blue says.
This?
Yeah, and the
Excellent.
You should just put it into the little thing.
I don't know. Nope. I don't even know what was written there. What is it?
Hit back. 143.
143, which makes sense. That is really big. So 146, it's 238. This is 3 less, so it's also 3 less. I just wrote down what those were, Riley. I just wrote mass number beside that and atomic number for someone who needed it. You don't have to write it in there. If then you wanted to make a nuclear weapon, here's how you do it. And if you have enough of this, it just blows up on its own. It's called a critical mass. And when you get critical mass, the reason is there's a variety of forms of radiation. But let's say you have an atom of uranium, and it gives out a neutron as part of its radiation, and it hits another atom. When it hits it, this one gives out 3 neutrons. And then each one of those hits an atom, and they give out 3 neutrons. Do you have to write this down? No. So you get a chain reaction, and very quickly all of it blows up. And the reason you need a certain amount is some of these, if you have a small amount, will be on the outside and won't hit another atom, and they'll actually just pass through and escape into like the atmosphere. So you only get a chain reaction when you have enough put together. So what they would do is they would get an amount just under the critical mass, get another amount just under the critical mass, and then really all you have to do to blow things up is clap your hands. If you're building a bomb, you get it in a piece of metal and you machine out a hole, and then you get another piece that fits that hole, and then when you fire one into the other, boom. Really easy to make. However, these have exact same chemical properties. You have far less of this than that. How could you separate these? You just have a chunk of uranium. You can never get to critical mass with just the ore because there's not enough in there. There's too much of the other stuff. What property would you have to use to separate out the 235? Yeah?
Radioactiveness?
You can't actually, we don't have anything that pulls only radioactive elements. If we did, that would be fantastic, but there's no magic sponge that'll like suck those up. Chemically, they're the same. They react to like solvents the same. They dissolve the same. What is the only difference between the two? Weight. So to separate by weight, you know, you've heard of panning for gold? And then the heavy gold sits at the bottom. A really efficient way of panning is called centrifugation. We just spin it really fast, and all the heavy atoms go to the outside. But to do that, this is solid chunks. We want atoms. So you heat it to a gas, then you spin it really fast, then you pull off all the heavy ones because they're coming to the outside, and you're left with a 235. It is really technically difficult. This is not something a grade 11 student would be able to do. This is the hard part of making nuclear weapons. So if you're a country and you want to make nuclear weapons because you would like to join the nuclear club, you have to get really good at centrifugation. And it's enough of a worry that there was a virus in the early 2000s that was on everybody's computer at one point, but it didn't do anything. It didn't do anything bad. It just sat there. Nobody knew what it did. It spread itself really well. And they're like, what is this thing? And then eventually they found out. Because in Iran, I think, nuclear program, when that virus got into their centrifuges, it just messed it up a little. So it never quite worked properly. So it was probably designed by a major government to slow down the ability to make nuclear weapons of an opponent. So CIA, CSIS, IDF, some sort of secret organization. How many of you have heard of CSIS? One person. How many people have heard of the CIA? This is why CSIS is better than the CIA. What is CSIS? Yeah, Canadian CIA, FBI. And the Canadian version you've never heard of, so obviously they're better at secrets.
Or it's not very good at reading.
Aha. Nicely done. Okay. This is repeating some of the things I've said, but just as an illustration, you have no notes on here. I'm just going to point it out. Because this is something that students make mistakes on, even in Chem 11, the difference between atomic mass and mass number. So the atomic mass, as I've said, is an average. But if we take as a specific example, the atomic mass of bromine is 79.9, and you would think, oh, I'll take the I'll round that to 80. There must be a bromine 80 that exists. It turns out bromine exists as 79 and 81 in roughly 50-50 amounts. So the average comes out to 79.9, but there is no bromine 80. It doesn't exist. You get bromine 79 and bromine 81. And so that's why when you're doing like advanced chemistry, you want to be very careful about what you're doing. If you are spending money to help families of Canada and you're the Prime Minister, Trudeau would say, oh, 2.3 kids per family. So we'll put out resources in that amount, multiply the number of families, you're fine. If, however, you're going to someone's house and it's a potluck and you only bring enough food for 2 kids and they have 18, probably you need to use their actual family. Any questions on the difference between atomic mass and mass number? Yes?
How do you find an mass number that one periodic table?
You can't. You have to be told it. In the same way that if you're going to someone's house, you can't figure out from the Canadian average what their number is. Someone has to tell you. But the next one is where I tell you. I want you to fill out this table, and I'm going to tell you. So I'm going to write some numbers in, and I want you to fill the rest. I'll do the first one, but if you already know how this works,
I
you can
think
start.
or at least I'm too stupid for this.
No, you're not. I'm going to show you how to do the first one.
Oh, wonderful.
Yeah, no. But I gotta. But you would be correct in thinking that you couldn't do it right now, because right now there's nothing written there, so you have no idea what to write. So for the first one, we are going to do. I need a much thinner line. So this is oxygen 18. This is chlorine 58. Let's make this one 15 protons. Mass number 31. Next one, it's going to have an atomic number of 6. And the number of neutrons is going to be 7. Neon, let's see. I'm going to give the next one 10 protons. 22 mass number, yeah, you'd need that. And then 34, oh, wrong spot. That's not gonna work. Ugh. I made it really big, and that's kind of annoying. Purple again, and the really small one, thank you very much. And, oh, and the last one's lithium 7. That's a dash there. I will put it like this. And I'll just give you a second to copy all those down, and then I'll tell you how to do the first one. Yes?
Don't we need for the 34 though? Don't we need another number?
No.
State
Because if you don't know it, where do you assume it from? Yeah. So in some cases, you aren't given it. So like if you're invited to someone's house and you knew they had kids, but you didn't know how many, you'd be like, oh, I'll assume they have 2 or 3 kids and you bring enough because that's the average. You wouldn't assume they have 18. My grandparents had 10 children. My parents had 4. We stopped at 2 because 2 is way. Kids are like, nowadays, you'd have to like send all of them to Brentwood. It's a requirement. It's like how much money? It's like pushing a new car into the ocean every year. But does anybody know, worldwide, the number of children given per family is going down? Does anybody know why? Why did people used to have a lot of kids? Yeah. We didn't have antibiotics. We didn't have good prenatal care. I know my grandparents had 10 kids, but I also know that 4 of them didn't survive. Pardon?
People actually want to that's the
People actually wanted. That's probably true, actually. Yeah, because like kids cost money, and back then kids are what helped you survive in your old age. Like there's no pension retirement benefits if you have enough kids, and you're going to be okay because they're going to kind of help take care of you. And if you want to be guaranteed that there's 2 kids at least to take care of you with an infant mortality rate, I can't remember what the percentage was, but back then, how many kids did you need to have in order to guarantee, like 99.9% certainty that you'd have? And the answer is something like between 8 and 10, like it's a large number. And that's not like you'll end up with more than 2, but like there's like a 60% chance you'll end up with more than 2. If you want it guaranteed, you have to have a lot more kids. As infant mortality drops, we can see in the graph worldwide, the number of kids people have drops right in proportion to it. And they're expensive, I think, as Riley pointed out. Like, you have to send them to Brentwood, it costs a lot of money. Okay, first one I'll do. Some of you have already gotten started. If it's oxygen 18, what is its atomic number? Yes, Julian. 8. How'd you get that? Number of protons. And how'd you get the number of protons? How'd you know from this it was that? Shows in the periodic table. You just look up oxygen. And if it's the atomic number is 8, what's the number of protons? 8. What's the atomic mass?
16.
It is 16.0. What is the mass number?
16.
18.
18. And I fooled you in that one because for some of these I have given you a mass number, so it'll be different than the atomic mass. And that's just to emphasize it. So which one of these numbers do you use to calculate the number of neutrons?
The atomic mass.
Mass number. Always this one, if you have it. If you don't, you can estimate it. But you, in all of these but one row, in some way I've given you a way to calculate that out. So what is the number of neutrons?
10.
Number of electrons? Why?
10.
It's 8. Why 10? You're,
Oh, so that was an ion.
oh, no ions in this one. So if you're an atom, your electrons should be the same as the number of
Protons.
protons. So there's actually 3 columns in here that should be identical. And then the symbol for oxygen,
Oh.
O, and I want you to include the mass number in the proper spot. So it'd be O with an subscript of 18, not subscript, superscript of 18 beside it. So I've done the first row. Do the I think I'm required by law to say I'm not allowed to say do this for homework because you have no homework. But I'll probably say do it for homework on Monday. So we'll do it from there. Oh, your quiz next week will be on either Thursday or Friday, whichever day we have class.
We have
It will not because it will not be on what we did today. So at the beginning of the course, we did definitions, we did classification of matter, and we did the Bohr model. So you should be able to draw a Bohr model. You should be able to use the definitions of the terms that you were given. But anything we did today, because we don't have a prep, will not be on your quiz.
Sorry, what-
Yes.
When will we get our
50, was that?
Oh God, as soon as I've done it, hopefully soon. It's in a bag well, half of it's in a bag in my office, and I'm hoping to start it today.
fabulous?
Yeah.
Wait, so will the quiz be forwarded or summative?
That's a more complicated question that I can give while people are running out. But if you want to know the answer, all quizzes are summative until they're formative. Do you know what I mean by that, though? What do I mean?
Until the class, all the class fails.
Kind of, yeah. So if we've only done one quiz, then that's kind of your mark. However, if we do a test that covers the same material and you do better on the test, then the quiz becomes formative because you show you learned. Does that make sense? So, I'll count it right away because why not? It's the only thing I have. But if you do better later, I may discount it because you did better later. And if you do worse later, I might keep it. So I do it in a way that overall will help you in the future. Does that make sense? Okay. Yo,
Definition of the
you guys come. Oh, so phone rules in this building. You are not allowed to take it out at any time, including sitting in the classroom, in the building. If you go out, you're using like you're going to the library, you're just going to sit and work. When you sit down, if you're just going to do work, you can pull out your AirPods, you can pull out your phone, you listen to music, you can do any work, that's fine. If you're in a classroom and the teacher says, oh, you're like, hey, can I listen to AirPods while I'm doing my work? The teacher says, yes, you can pull out your phone, put in your AirPods. But it's not by time anymore. That was the new thing this year from Miss Allen, is that it's by place. So not out until invited to, or you're like grade 12 is spare, so if you're sitting down there. Or if you're working during tutorial out there and you listen to your AirPods, fine. When you walk in the door, no AirPods on the phone.
So what if we're like not in the building and the class hasn't started yet? If we're just like sitting outside on a bench, can we go?
No, yeah, that is fine. Yeah, as far as I know, yeah. It was just the academic buildings. They actually said, yeah, we're going to do this like we always have done. And I went, but that's the rule for now. Yeah, you can do that. I had a chat with your house parent. He thinks that you'll learn well from this.
I was just like using it earlier as a translator and stuff.
Oh,
Yeah. Just like translating.
did I
words.
talk to you about this?
Yeah, I ordered one.
Oh, cool.
It should arrive like sometime next week.
Okay, just ask me during class.
Oh, okay.
Because you can be given permission by a teacher to do anything. Like, it's like if you're in the middle of a bank at 3 a.m. and the police break in and like, what are you doing here? And you're just like, I have a note from my mom. You're good. It's fine.
Is the library still running?
No, I got you.
I was gonna go
At
copy
least-
paste all the names again.
Yeah, no, it's off. Yeah.
Alright, see
But-
you on Monday?
See, I think if we have it on Saturday, we're then on Monday, which I think means our quiz will be on Friday. I'll post it in the Google Classroom as well.